Hey, all right. Well, delighted to introduce Ryan Hahn to talk about how to do a literature review. Take it away, Ryan.
Hello. Okay. Good. All right. Um, yeah, so in this session, we're going to be going over how to conduct a literature review, and specifically how to do so in a way that enables you to effectively write a related work section. So by the time we finish today, the hope is for you to be able to, one, conduct a literature research to identify papers relevant to whatever topic of interest that you have, to be able to read a machine learning research paper, as well as summarize its contributions and takeaways. And finally, being able to summarize previous works in your given area into actual related work section that you can have in your paper. And to give you a sense of why this is an important part of the research process, I thought it would be good to give you an example. So this is a picture that I got from Twitter. And what you're seeing is actually part of a professor's Halloween costume. So this professor, a machine learning professor, showed up to his lab's Halloween party dressed up as a reviewer too. And for those of you who are not acquainted with the scientific meme literature, reviewer 2 is this famous inside joke representing the grumpy and aggressive reviewer that you always seem to get during peer review. So if you look at the photo, there's essentially a list of ridiculous comments that you'd never want to receive on your paper. But the comment that I wanted to highlight in particular is the one describing your work as incremental on there. And this one's actually a little bit more serious than the rest of the comments because it's legitimate grounds for rejecting your paper from publication, at least from high impact venues. So to demonstrate, if we look at the criteria for publication at a top scientific journal like Nature, they specifically require papers to be of outstanding scientific importance. And similarly, if we look at the criteria for acceptance at a top machine learning conference like NeurIPS, they're looking at least for a significant and novel contribution. So in other words, if you want to get your research published, you need to be able to actually convince your audience and reviewers that your work is novel. So in other words, you need to be able to, first of all, make sure you're doing novel research as well as communicate that to your audience. And the difference between receiving the comment that your work is incremental and novel can often boil down to how well you can understand previous work and communicate that. In other words, how well you conducted your literature review. So a lot of our time in this session is going to be focused on actually practicing the steps of a literature review. But here's a high-level overview of what we're going to be going over today. So first, we're going to be going over how to conduct a literature search with different search tools and strategies. Then we'll be going over how to read a research paper, as well as efficiently extract the main points. Then we'll be going over how to keep track of papers, because as you're going through a different field, you want to keep track of what you read, as well as how to organize and summarize previous works. And finally, how to actually take all your findings and put that into a related work and communicate that to others. So science is vast. Here's a visualization of recent science. And in this visualization, you can see it's colored by different disciplines. But there's roughly 20 million papers that have led to over 2 million patents. And while there's about, I don't know, like a dozen or so disciplines here, there's over 500,000 subdisciplines represented in this graph, with roughly 200,000 clusters lasting 2 to 16 years each. So it's really awesome, I think, and breathtaking in the sense that, like, here's probably my best work is somewhere over here, some tiny little dot in the massive vastness of science. So you can imagine why literature search might be such a difficult problem, because no one has the time to get even through any reasonable fraction of these papers if we just try to go through all papers ever. But thankfully, there's a variety of search tools that are very helpful. And specifically, here's a subset. So we have papers with code, Google Scholar, Semantic Scholar, Reddit Machine Learning that are very helpful for AI literature specifically. There's a variety of other tools that you might be familiar with, such as PubMed, but those are more broad. But these are a specific subset that can be very helpful for AI research or AI in healthcare research. So the first thing that we want to do is construct a search query when we're using one of these search tools. So essentially what this consists of is for each concept that we're interested in, we want to create a list of search terms that includes synonyms. So for example, you might go from electrocardiogram to electrocardiograph. Abbreviations. So electrocardiogram can be abbreviated as an ECG. Related terms. So something similar to self-supervised learning might be contrastive learning, as well as different spelling variants. So there's often differences between, British and American English and other sorts. So ECG to EKG is a good example of that. And once we have our list of concepts, our search term might be electrocardiogram and self-supervised learning. We want to combine these different search terms using OR. So within a concept, so that would be like electrocardiogram or ECG or EKG. And then between concepts such as electrocardiogram and self-supervised learning, we want to combine those with AND. So our search term might look like electrocardiogram and self-supervised learning. And these are often we need to be careful with this because a lot of the times these are implicit actually when we're constructing our search queries. Especially and is often but not always implied. For example, if we just search high school students' test scores, this is going to be interpreted as high and school and students and test and scores, when in reality we probably meant high school students and test scores. Similarly, I guess most of us have a computer science background, so this one might be a little more obvious. But and is usually the primary operator. But this can often get lost on us when we're actually constructing a search. For example, high school students or secondary students and test scores or test results was probably intended as high school students or secondary students and test scores or test results. But without these parentheses, that's not how the computer is going to interpret the search. And finally, the minus sign, at least for Google Scholar, excludes a term from the search. So if we wanted to search, for example, electrocardiograms, but not echocardiograms, we could search ECG minus echocardiogram. And that would limit our results to only those with ECG and not the term echocardiogram. So one other strategy that I wanted to mention before we actually dive into a live search example is snowballing, which is basically finding related papers once you found a paper that fits your interest. And you can do this in two ways. First is by looking at papers that the paper you're reading cites, and the other is looking at papers that your paper is cited by. And we'll go over a few examples of ways to do this with search engines. All right, so time for the first live example. So you can probably tell from the examples that I used on the previous two slides, but some of my research interests lie in self-supervised learning for electrocardiograms. That being said, the field has changed a lot recently, so that's actually the topic I'm going to be using today throughout most of our live examples. So usually when you're constructing a search query, this is often an iterative process. For example, we might try electrocardiogram and self-supervised. So this returns about 1,000 results or so. And this is more of an art than a science, but you might want to just keep adding terms until you're satisfied, I guess, with the coverage that you have. We won't spend a ton of time to this today, but for example, you want to do self-supervised or contrastive, as well as we can just add a few synonyms and abbreviations for electrocardiogram. Let's see, or ECG or EKG. All right. That looks like that returns roughly double the number of results, but we'll use that as our starting point for today. So going back to snowballing for a second, there's a few helpful tools in Google Scholar that you can use to find really good papers. So if the paper that we were interested over here is, patient contrastive learning, for example, we can use the Google Scholar cited by. So if we click this, it'll give us a list of papers that cite patient contrastive learning. So that's the way we can forward snowball. As well as there's also this related articles tool that's usually a bit broader than just using the cited by. And similarly, one other tool for snowballing that we can use is actually Semantic Scholar. So if we take patient contrastive learning, for example, and search it into Semantic Scholar. Semantic Scholar has this list of citation references, and they often have this highly influenced designation if their algorithm determines to be a citation that the paper is heavily based off of. So looking at this specific paper, this one doesn't seem to have a highly influenced one, but let me just choose another paper and see if it has one. Let's try this paper, for example. Okay, this one doesn't either. Let's try one. Okay, so looks like none of these papers were very highly influenced by specific one. But just to give you a sense of what that actually looks like, let me pull up one of my previous papers. This one. Okay, that's very interesting. Not sure why it's not showing up. It was earlier, but we'll come back to that and I'll see if I can figure out what's going on there. So other than that, in general, we want to use our search strategy to find about 15 relevant papers in order to get a good grasp on a topic. But usually this is not going to be just the first 15 papers that the search strategy yields. Instead, generally a better idea is to scan a few papers and then decide which to read more. So that's what we're going to be going over next. So moving on to how to actually read a research paper and strategies for that. So often the temptation when you first come upon a research paper is to read everything. And usually you'd imagine when we come upon a research paper, we want to read it from end to end and start annotating and understanding everything. But this is really almost always not the best way to read a research paper. When doing a literature search, at least, because this can take hours per paper and is not necessarily very efficient. So deep reading has its place, but it can actually be actively harmful during the literature search stage. So what is the best way to read a research paper? So people have different variations on this, but there seems to be a general consensus that reading in passes is a great way to extract value from research papers, and with later passes being reserved for more valuable or relevant papers. So in general, the first pass that you want to do is basically making sure that the paper is relevant. So usually you can do this by just reading the title, the abstract, and the figures, and it'll become pretty apparent soon whether this is the paper that you're looking for or not. Next, you might want to understand the paper's methods and findings at a high level. So this can vary depending on the structure of the paper and how the authors formatted it. But typically this requires reading the introduction or maybe parts of that, as well as the experiments, figures, and conclusions. And finally is a deep reading where you read the paper in its entirety. So there's just a few questions that might be helpful to think about while reading that kind of give an overview of considerations you're making during those first three passes. First might be, what did the authors try to accomplish? What are the key elements of the approach? What can we actually use or take away from the paper to inform your own work? As well as what references do you want to follow? So now we're going to take these ideas and try it as an actual live example for reading a paper. So looking here, so there are generally different formats for reading research papers. Usually there are scientific journal formats, as well as machine learning conference formats. Because we're trying to read a machine learning research paper, let's see if I can find one in a machine learning format. So generally, archive papers for machine learning research are in the format with their methods first. So let's take a look at this one. So let's see, patient contrastive learning, performant, expressive, and practical approach to ECG modeling. Okay, let's see if we take a look at the abstract. They talk about supervised machine learning being limited due to scarcity of labeled training data. Latent representations. Let's see. Okay, so this model does seem to be relevant to what we're looking for, because they are in fact working on electrocardiograms, and they're working on contrastive learning, which is usually used as a subset of self-supervised learning. So let's see, if we take a look at the figures. So here's an overview of their, here's an overview of an example workflow that you use. So they seem to be taking electrocardiograms with a given label. They use PCLR to somehow embed these electrocardiograms into representations. And then they use the representations for self-supervised or some sort of clinical analysis. Let's see, if we look at the rest of the figures. So this is a methodological figure that gives an overview of how they actually do this. And I guess the core idea here is that ECGs from the same patient should be similar with regards to the representation, and ECGs from different patients should have different representation. And this seems to be an overview of their encoder. Okay, so this seems to be relevant. So that this could be our first pass verifying that this is indeed what we're interested in. So for our second pass, we might try to understand the methods and the findings. So we're going to come back to a deep reading of this paper later, but I actually wanted to give an overview of how we might, store our findings when we're going through different papers first, and then we're going to go through this paper as well as a few other papers, and try to extract value out of them. So going back to the slides, yeah. So keeping track of papers. So there's a few different considerations to keep track of. Well, first is just the title. And the next would be a problem. And sorry, I forgot to mention. So this is kind of like a formalization of previous questions that I found helpful. There's a variety of different, depending on your interest, there might be different data elements that you're trying to extract. But this is just a generally useful format for extracting. And usually you want to organize these in some sort of spreadsheet format. So once again, we might want to look at the title of the paper, as well as what is the fundamental problem that the paper is solving and why does it matter. Next, we want to look at the prior assumption. In other words, what makes this research novel? How does it differ from previous research? And namely, what did previous research do that was inadequate? Next, we want to look at the insight. How does the paper propose to fix this inadequate prior assumption? Next is a technical overview. How did the paper actually implement that idea? Next is evidence. In other words, what evidence do the authors provide to show that the idea works? And finally, what's the conclusion? Or in other words, what's the impact? How does this actually change how we think about the problem? Yeah, so going back to the live example, I have a paper tracking template here with just columns representing each of those fields that we just went over. This should be available in the notes for this lecture. But if anyone would like it, just let me know in the chat and I can send it. But so going back here, if we look at PCLR, so let me just track this as our first paper. Right. So the problems, so in general, I don't think we're going to have enough time to go over many papers in depth. So we're not going to be able to go all the way to the end. But I'll try to give an overview of just, how we might try to answer these questions in an efficient manner for different research papers. So let's see, supervised machine learning applications in healthcare are often limited due to a scarcity of label training data. So this seems to be the problem that the paper is trying to solve. So let me just take this out and put it in here. Okay, so next we're looking for the prior assumption. In other words, how did previous work work to solve this problem, if any at all. So it looks like previous work has tried to do pre-training in order to solve this example. I'm doing a few labeled training examples. Then they describe what's an ideal pre-training strategy. Let's see. With it being performant, expressive, and practical. And this seems to be the prior assumption that they're going to highlight. That previous pre-training strategies in healthcare have focused on this first goal, with a few notable exceptions that also consider the third goal. So in other words, they all focus on maximizing performance on the limited training data. As larger groups adopt resources, we therefore develop. Okay, and this seems to be what that actually looks like, that these feature vectors are optimized for linear models, making them useful out of the box. So I'm going to take this out, put it over here, prior assumption, pre-training strategies. I focused on performance. Rather than they describe multiple tasks and being practical. Expressivity. And the insight that they provide is that their fundamental task is going to be centered around patient identity over time. Patient-centric latent representations. Okay, so I'm going to write this down as the insight. Patient-centric latent representations. Enable generalizability. So how do they do this technically? Let's see. So if we read the methods here, okay, it seems to be a standard contrastive learning setup. With essentially their selection function being based on whether they come from the same patient or not. So for those of us who aren't familiar with contrastive learning, we might be able to go back and read the related work. So just skimming here, it seems to be, so deep learning has been applied on electrocardiograms for a variety of different tasks. As well as so contrastive learning is a self-supervised learning method that requires training data to be labeled with notions of positive pairs and negative pairs. So positive pairs are data that go together, and negative pairs are data that are distinct. So it seems positive pairs, we want to have similar representations. So I guess we'd have some sort of prior expectation that they should be similar, and negative pairs should have dissimilar representations. And so their insight seems to be that ECGs that come from the same patient should have similar latent representations, which makes a lot of sense. Patients should ECGs the same patient should have similar latent representations. So how do they actually do this? So their loss function seems to be, they use a contrastive loss, so normalized temperature scale cross entropy with an indicator function that's true between positive pairs coming from the same patient. And they use this by doing patient indexes. So contrastive loss over and they do this with standard. It seems to be, they don't make any claims for novelty for their encoder, so that doesn't seem to be new. They have a projection head. So let's see, we went over their selection module, we went over their encoder. They also have a projection head, which projects ECG representations into a space where the contrastive loss is applied. So I guess after they push it to their encoder, they apply a projection head. And then contrastive loss we already went over as well. Great. So then the question is, what evidence do they provide that this actually works? So this is typically in the experiments and the figures. So this is describing their cohorts. So this might be, information that's very important for a deep read. But once again, for time, we're going to try to go over this a little bit quickly. Let's see. So for results, they show PCLR is better than a model trained from scratch for 4 different tasks. So they do atrial fibrillation classification. What is this? Left ventricular hypertrophy, I would guess, classification, sex classification, age regression. And we're looking over different amounts of training labels. And we see that PCLR outperforms the model that's trained from scratch across all these different label fractions, with the gap being bigger at these smaller label fractions. They also show linear models trained on ECG representations. So I guess the first one is showing that pre-training is better than just supervised training. This next experiment seems to be going over that deep ECG representations coming from PCLR are superior to just standard, I guess, non-deep learning electrocardiogram features, as well as this different rhythm classification training encoder. So pre-training is better than this other method of pre-training. That's not self-supervised, that's training on another self-supervised task. So, okay, so let's note those 3 down. So first, they show that it's better than an encoder trained from scratch. Better than encoder trained from scratch on 4 tasks. Next, it's better than standard ECG representations. Traditional ECG features. Next, it's better. Let's see. Next, it's better than rhythm pre-training. And the data sets that they use for this are roughly 10,000 ECGs from 2 different sites, or they pre-train on 400,000 ECG, 3 million ECGs from 400,000 patients, and they seem to do other tests on this smaller data set from Brigham. Okay, I guess the impact, well, what seems clear is that from their figures, is that PCLR outperforms PCLR, patient-centered pre-training, provides value. It's not clear how this method compares to other self-supervised methods. compared to no pre-training. But it is clear that there's a lot of value compared to no pre-training. Yeah. So going back here, I think there were two interesting things mentioned. So the first seems to be that this is essentially an adaptation of a method from a previous paper known as SimCLR. So let's take a look at that one, because that seems to be kind of the seminal paper for contrastive learning. So let's go here. So this is an example of snowballing that we're doing here. And I realize we're running out of time faster than I expected, so I'm going to try to pick up the pace. So let's go through the title real quick. A simple framework for contrastive learning of visual representations. So this is not with regards to the ECG domain, but it seems to be, according to the related work, this was kind of the seminal work for contrastive learning or self-supervised learning that we're interested in. This paper presents SimCLR, a simple framework for contrastive learning of visual representations. They do contrastive self-supervised learning without specialized architectures or memory bank. They show data augmentations. Okay, I guess so the major takeaways here are that composition of data augmentations plays a critical role in defining effective predictive tasks. Introducing a nonlinear transformation, so I guess that's similar to the projection head that PCLR talked about, substantially improves the quality of learned representations, and contrastive learning benefits from larger batch sizes and more training steps compared to supervised learning. So this seems relevant to at least understanding the underlying methodology going on here in the field. So let's go through this one quickly as well. So the problem seems to be, I guess would be the problem here, as earlier mentioned, that previous contrastive learning algorithms require specialized architectures or a memory bank. And why is this actually a problem? Let's see here. Pixel generation. If we look at their related work, for example, they might talk about that. Okay, so they don't, okay, related work over here. Contrastive visual representation learning. I see. So, okay, I guess they don't elaborate or expand upon why this is better. Other than it seems to be, I guess, from the title that the simplicity of this approach as well as performance is why it's better. So problem, because this is a self-supervised learning setup, this is also about supervised machine learning. Algorithms are heavily label dependent. And the prior assumption seems to be that self-supervised learning algorithms should use specialized architectures for a memory bank. And the insight that they seem to be providing is, rather than depending on these specialized features, they can have a very simple framework. And by composing these different augmentations together, they can outperform previous methods. So the insight seems to be here that composing simple data augmentations is enough to learn related representation. As far as a technical overview, let's see. So the parts that they highlight is a data augmentation module, encoder, projection head, and traceable loss. So this seems to be the same for parts that were highlighted by PCLR. So I'm not going to go too much into that. But let's see. Contrastive loss data augmentation module projection. And they seem to be sampling in many batches. They do not sample negative examples explicitly. Okay, so I guess one of their contributions is that the way they actually choose these contrastive pairs is with a mini batch. Contrast loss, choosing contrast pairs with a mini batch. The evidence they provide is, let's see, examples. Okay. Number of parameters, top one accuracy on presumably ImageNet. So they show that their pre-trained algorithms use for a similar number of parameters. So a similar spot on the x-axis, they have significantly higher top one accuracy than supervised models, and this seems to be true especially for supervised models are up here. And they seem to be able to get, just using pre-training, they seem to be able to get closer to supervised performance with larger models. So big takeaways: contrastive learning needs stronger data than supervised learning. Composition of data augmentation is important. Let's see, where did they? Okay, so over here. So first of all, they show that as they increase the strength of the augmentation, supervised, the performance increases, and that this effect seems to be more prominent for self-supervised learning than supervised learning. Then they show, let's see. Okay, they show that batch size matters a lot. So increasing the batch size improves performance across all these different numbers of epochs, as well as they show that SimCLR outperforms previous self-supervised methods, as well as supervised methods substantially, especially for lower label fractions. And finally, they seem to be showing that SimCLR is significantly superior to supervised learning across a whole wide variety of data sets and tasks. So I think that seems to be the main takeaway that I want to highlight here. So SimCLR outperforms supervised learning. As methods wide the tasks. And as far as the impact, it seems like the crucial parts of this are composing data augmentations and restraint. Composing data augmentation and augmentations is useful for representation. Contrastive learning. So another way we can snowball is if we go back to this, let's see, PCLR paper. They seem to talk about, okay, so I guess PCLR was not the first paper to try to apply SimCLR to 12-bit ECGs. So they have this paper over here. They show improved performance in rhythm classification compared to other pre-training strategies. And they have a variety of others for other modalities. But this paper seems to be very relevant to what we're looking for. So this is contrastive learning. Cardiac signals seems relevant to what we're looking for. All right, so this paper also mentions patients. So let's look at the abstract and figures real quick to see if it's indeed relevant. Healthcare industry generates troves of unlabeled physiological data. Okay, seems to be solving a similar problem. This data can be exploited by contrastive learning, self-supervised pre-training. Encourages representations across space, time, and patients. So in this one seems to actually be broader than patient contrastive learning, but they might have a different approach to how they implement that. And they show that it outperforms other state-of-the-art methods. I'm assuming these are not from, these seem to be just general computer vision methods on linear evaluation, fine-tuning for different downstream tasks. Okay, so this seems to be very relevant to what we're looking for. Let's see. So the problem seems to be healthcare data, unlabeled healthcare data is not exploited. It's not being exploited. So for their prior assumption. This might be in their related work. Self-supervision for medical time series. Okay. Okay, so our work focuses on identifying commonalities across both spatial and temporal components of data. This seems to be one of their key insights. Key patient. A family of patient-specific contrastive learning models and evaluate them in 4 distinct data sets. Gotcha. So their main argument here seems to be basically combining approaches from different fields of thought. So we have contrastive learning in general, as well as self-supervision for medical time series. I guess this might have been an earlier paper, seeing as how they don't cite previous work for electrocardiogram contrastive learning. So let's see. So their prior assumption seems to be works from other modalities focused on spatial, temporal, or patient-centered representation with their combination. And their insight is combining space patients for contrastive learning. All right, so technically, how do they do this? They have positive and negative pairs of representations. They have transformations or augmentations, as well as contrastive loss. So let's see, so they have temporal invariance. So it looks like 2 different ECGs from the same recording should be treated as positive pairs, makes sense. Spatial invariance, so different leads from the same ECG should be treated as positive pairs, but there's some sort of similarity there. Makes sense as well. So that's CMSC, CMLC. And then their last method seems to be combining these 2 methods into one. So let's see, how do they actually implement this? They do mini batching like SimCLR. Okay. They have a similar indicator function to PCLR. Great, so let's see. Positive pairs should can be defined as segments coming in you reporting at time. States. In terms of evidence, they have a similar setup to SimCLR where they're looking at the effect of different perturbations, it looks like. And they show that for 2 different data sets, their methods of CMSC, CMLC, CMS, LLC have significantly higher AUC at the half label fraction than these other previous self-supervised methods. They also show, let's see, looking here, that it's superior to supervised learning. So this one seems to be, this is linear evaluations. They just train a single layer. They also look at fine tuning. And it seems for both linear evaluation and fine tuning, their methods outperform previous self-supervised methods as well as supervised methods. Finally, they show that their method leads to similar representations. Let's see, so SimCLR doesn't seem to distinguish between intrapatient and interpatient, but their method actually has a different distribution for distances between intrapatient and intrapatient. So just writing this down real quick. Methods outperform. For both linear evaluation and fine tuning. The impact seems to be time, space, and patience. Let's see. Mutual information exists across time, space, and patience, and can be leveraged. Gotcha. So let's just try to skim through maybe one more paper really quickly, and then we're going to try to go back to the slides and how to actually write this up. So normally you do this for a lot more in depth for each one of these papers, as well as for about 15 papers or so. But for the sake of time, I'm going to try to just find one more paper to skim. So let's see, going back here. Let's see if we can find another machine learning paper. So over here. So lead agnostic self-supervised learning for representations of electrocardiograms. So this seems to be very relevant to what we're looking at. Recent years, self-supervised learning methods have looked at only global representations, but they're looking at local representations as well. In addition, we propose random lead masking as a new augmentation. So this seems to be relevant to what we're looking at. Let's see if we can get the PDF. Okay, so lead agnostic self-supervised learning. The problem that they seem to be saying is, let's see, pre-training with unlabeled data has proven helpful. So in other words, if we flip that on its head, unlabeled data is being exploited, so very similar to clocks. I'm just going to copy that. The prior assumption seems to be that previous works have only focused on using global contextual representations. And the insight they provide is using both local and global contextual representations leads to better generalizability and performance. So how do they actually do this? Let's see if we skip ahead to their experiments, maybe. So they seem to do this by combining CMSE, I guess that's from clocks, with Wave2Vec 2.0. And they show by combining these methods as well as with the random lead masking that they propose, that this leads to significantly better performance than these previous self-supervised methods, which only focus on global contextual representations. So they show this for different lead combinations, as well as for, so this, okay, once again, this seems to be, let's see, what's the difference between these tables? Fine tuning over here. An individual model. Okay, so this is for one 12 lead model for all these different lead combinations. And here they seem to be having a single model for each lead. They also show, okay, for diagnosis classification and patient accuracy. So I guess the takeaway here is, so let's see, CMSE plus Wave2Vec seems to be their contribution there. And the evidence they provide is across different coders, single lead versus 12 lead. New method significantly outperforms previous SSL methods only in global context. And the impact here seems to be global and local context should be utilized for self-supervised learning. So how do we actually put this together into a related work? So I'm going to skip through a few slides here, but essentially the goal of a related work is to communicate how your research differs from previous research, as well as show that you have a good understanding of previous research. So how we might want to actually do this is to group the papers in your spreadsheet looking for shared assumptions or approaches. This is going to be a little bit difficult because we only have 4 or 5 works there, and summarize each group in one paragraph. Finally, we want to order the paragraphs, typically branching out from high level to lower level. For example, we saw previously that a lot of papers were looking at how does contrastive learning work in general, as well as specifically with regards to ECG modalities or maybe a subset of that. And then finally, we want to bit flip each paragraph. In other words, I skipped over this earlier, but it's essentially inverting the assumption that the previous methods make and showing why your research is different and summarize this at the end of each paragraph. So if we look at the works that we've looked at so far, there's a variety of different groupings we could make. It's going to be harder because there's there's only 4 of them. But one trend that does appear to me is it seems like SimCLR, that they looked at the evidence they provided is showing that SimCLR outperforms supervised learning as well as self-supervised methods across a wide variety of tasks. Whereas these 3 ECG works, once again, can't tell if this is just because of the sampling size that we were using, only looked at a much smaller subset of tasks. They looked at somewhere between 1 to 4 different tasks. So I guess that's one bit flip we could show for evidence if we wanted to show that differently for our research paper, as well as if we look along methodological lines. So all of these works seem to be making the assumption that contrastive loss is contrastive loss with various sorts of mutual information exploitation are the best way for running representations for ECGs. So it could be the case we would have to do some more literature search to understand, but it might be worth exploring whether there are other works that have leveraged other sorts of self-supervised learning besides contrastive learning, electrocardiograms. So as to how we might want to write this up, if we were going to go down the first line, we might talk about self-supervised learning works in other domains. For example, we could talk about SimCLR or Wave2Vec and how for these other modalities, they've been shown to improve performance across a wide variety of tasks. And then next, we might follow up with a paragraph talking about electrocardiogram, self-supervised learning, and showing that while there's been a variety of different methods that have been tried and have been very valuable, that they haven't shown that it works across a wide variety of different tasks. Sorry for the technical difficulties at the beginning and how this kind of accelerated the rest of it, but I hope that was valuable and hope there were some takeaways for you.
Thanks, Ryan, for that wonderful walkthrough and overview of how to do a literature review. I'm sure that was helpful for many in the audience and a very critical part of all really research projects. So thanks once again.